Today what we're going to do is we're going to take a look at something called formal charges. And just because you can draw a molecule, just because you can make sticks and atoms and put them together, doesn't mean nature is at all obligated to follow that. So how do we know whether or not what we dream up could actually be a thing? Now there's a trick of mathematics that allows us to do this. It's called formal charges. So formal charge here, it's used to determine which structure is the best representation of the molecule. And it's not a real charge. It's not real. This is completely made up. We made this up, but it helps us to predict what molecules would actually exist. And this value is calculated. So we're going to do a little bit of math on this to be able to predict what actually would exist. And so, for example, we have 3 possible structures here for dinitrogen monoxide, 2 nitrogens and an oxygen there. There's 3 possible structures, and all of them follow the octet rule. And so it'd be like, oh, it follows the octet rule, must be good. Well, it turns out nature only likes one of these, and the others are just completely made up. And so how do we know which one is real? I know, fast forward to the slides, right? So we're going to use formal charges to figure this out. So what I'm going to do here is we're going to draw these molecules here in just a moment, and then we're going to do our formal charges. So let me go back here. So I'm going to draw these molecules here. So let me see if I can do this. You should write this in your notes and then put a little bit of space underneath there. So if you're at the bottom of the page, start over. All right, so we're going to go and we should have theme music. Okay, I think I did that. I think that looks like what we have up there. I hope looks pretty good. All right, okay. All right, now, formal charge. What is a formal charge? A formal charge can be used to determine the most plausible Lewis structure, so which one should actually exist. And the formal charge is equal to the valence electrons minus the associated electrons. So I'm going to say here, I'm going to say valence electrons, and then I'm going to say minus associated electrons. And if I take one minus the other, I end up with my formal charge. Okay. How do I do this? Well, to determine my associated electrons, I'm jumping ahead. Let's do valence electrons. Valence electrons, we should be good at this. We should be good at valence electrons. So, for example, did we end with you? It was Sam. Hey, Sam. And you're here. Oh, and Joel with the knees is not here. Oh, man. All right. I keep hoping. All right. Hey, Sam, could you help me find somebody? Somebody smart? Kara smart. Sam said so. You're in this class. If you're in this class, you're smart enough. There's like a test. You have to have like a math ACT and take high school chemistry and all that stuff. You're good to go. All right, so Kara, can you help me out? I need to know valence electrons for nitrogen. So if we look up on our periodic table, you find nitrogen up there? 5. Yep, okay, 5. So valence electrons for nitrogen is 5, okay? And what? How many? 5. Okay. 5 and 5. Okay. Thank you. It doesn't change. How about oxygen? 6. Okay. Wonderful. Kara. All right, Kara, thank you. Kara, I'm going to need help here in just a moment with my associated electron. So I want you to think of somebody, okay? So I'm going to call on you here, Kara, in just a second. Now, associated electrons. It tells us here that it's half of the atom's bonding electrons are associated with the atom. Okay, now that's kind of complicated. Here's how I do it, is I look at it like this. Now here I've got a lone pair, that's 2 electrons. And then here I've got my bonded pairs here. And my bonded pairs, each of these bonds is 2 electrons, like this. So there's 6 of them here. Now what I'm going to do is I'm going to make an imaginary box, and I'm going to say like this here. Here I've got my lone pairs plus half of my bonded pairs gives me my associated electrons. So how many associated electrons would I have here? That would be 1, 2, 3, 4, 5. I'm going to put 5 here. 5. Okay. Kara, I need somebody smart like you. Mariah. Okay, Mariah. Hey, Mariah. Hey, do you know what happened to Joe? He had knee surgery, right? Okay. Mariah, I'm going to need your help with the rest of these here. Okay? So Mariah, help me out here. I need to know associated electrons with this nitrogen. 4. Very good. Because there's 1, 2, 3, 4. Excellent. 4. And how about the oxygen here? 7. 2, 4, 6, 7. Nicely done. Oh, you're on a roll here, Mariah. 7, 4, 5, 6, 4, and 6. You are on a tear. We only let smart people into this class. Okay. All right, now what I'm going to do here is I'm going to just subtract these. So I'm going to say 5 minus 5 equals my formal charge. Now, Mariah, I need somebody smart like you. Allison, can you help me out here? 0. Okay. -1. -1. It's okay. I make mistakes up here all the time. If you come to class every day, you pick this out, right? I'm not picking on you. I'm not saying that you don't. Okay, help me out here. -2, +1, +1, -1, +1, 0. All right. Thank you very much. So now we've determined formal charges. We've got formal charges for all of our atoms in these molecules. Now, any questions up to this point? Ask her. Any questions? No? Off the hook. All right, so now we've got formal charges. What does that do for us? Well, our formal charges, let's see, valence electrons minus associated electrons. Okay, so to pick the most favored resonance structure, the one that nature is going to prefer, we've got some rules here. So for rule number 1, might be a good idea to write these down. So rule number 1, the best structure is the one in which the formal charge on each atom is 0. So best structure is the one where the formal charges on each atom is 0. And as I look at these, nope. Every one of these structures, yes, there's a 0 here and there's a 0 here, but these other ones are not 0. So we're going to need more than one rule. So rule number 1 is if all of them are 0, great. But if that's not the case, we need rule number 2. So if no such structure can be drawn, or if the structure is that of a polyatomic ion, then the best structure is the one with the most formal charges equal to 0 or closest to 0. So if they're not all 0, pick the ones that's closest to 0. If it's not all 0, pick the one that's closest to 0. Need another smart person. Evan? Right, Evan. Evan, help me out here. One of these two is not like the others. One of these two is not quite the same. One of these two has numbers further away from 0 than the others. Which one here has numbers further away from 0? The middle one. So Evan says this one here has numbers further away from 0 than the other two, because this is in the range of plus or minus 1, and here's -2 to +1. So out of these three, this is the least likely one, based off of rule number 2. So I'm going to go Evan says. Okay, nicely done, Evan. Thank you very much. Now, that gives us a tie here between this one and this one. Gives us a tie, which means we need another rule here. Last rule. Any negative formal charges should be on the atoms of the most electronegative element. Okay, so if we have a negative charge, it should be on the most electronegative element, which means we might have to go back to the last time we got together, and we had to identify where are our most electronegative elements. Now, Evan, I need a smart person to help me with this, or at least somebody who took notes from yesterday. Can you help me out with that?
Yeah, Buki over there.
Buki. Hey, were you here yesterday and you took notes? Yeah. Okay, help me out here. On our periodic table, if I had a periodic table, where are the elements with the greatest electronegativity? What direction? The top right, right? So as we get towards fluorine or helium, right? Those, Buki? Is that what your mom calls you? Or that's your nickname? Oh, but is it okay? Is that okay? All right, thank you. I wasn't sure if he's trying to pull something over here. So, okay. Between oxygen and nitrogen, which one is going to have the greatest electronegativity? Oxygen, because it's closest to that corner, right? So oxygen has the greatest electronegativity. So that means this one here should be good, and this one here should be pukey, okay? But Buki said this one. Am I saying that right? Okay, so this one should be the preferred molecule based off of all of our rules. This is what nature should do. All right. Any questions on that? No? All right, so then let me throw a couple of other ones here at you, a different one. We're going to take a look at something called the sulfate ion. The sulfate ion is SO4 2-. This is one of those polyatomic ions we should remember. And if we were to draw this Lewis structure, we have 5 rules. And the first rule of, remember the rules from Cosmo, from Fairly Odd Parents? Remember this one? There are 5 rules. The first rule is valence electrons. Hey Buki, I need somebody smart here. Can you help me out? Will. Over there. Will. We're just like back and forth. This is like tennis. Okay. Will, help me out here. Valence electrons for sulfur. 6. Right? And oxygen, 6. And there's 4 of them, so I'm going to go 6 times 4. And then I have these 2 here, so I'm going to add 2 more. And so if I add those all together, that's 6 times 4 is 24, plus 6 is 30, plus 2 is 32. Did I add that up right? Is it 32? Thank you. I can't do math in front of people. 32 valence electrons. Okay, so there's my number of valence electrons. And then, Will, I need to pick a central atom to do my structure here. Which would you choose between sulfur and oxygen? Sulfur, yeah, because it's the one, and then there's those other things, right? So we're going to put sulfur here in the center, and then we're going to make some single bonds like this, and then we're going to put our peripheral atoms on it, like this, and like that. And then our next rule is to complete the octet on these peripheral atoms. All right. And then I want to compare the number of electrons in my structure versus the number I predicted here. And so I go 2, 4, 6, 8. 8 times 4 is 32. 32. So it matches. I've got 32 electrons here, 32 electrons here. So I'm feeling pretty good. So now I want to do my formal charges to see whether or not this molecule is what nature had intended. So I'm going to start out then with my valence electrons, and Will, you already pointed this out. Oxygen is 6, and sulfur is also 6. I'm just going to go 6 and 6. And these others would be the same as like 6, 6, 6, 6. And maybe I'll write it out here just in case. Okay, 6. Okay. And then I need my associated electrons. Will, help me out here. Associated electrons on this oxygen. 7. 2, 4, 6 plus 1 is 7. Okay, so minus 7 gives me a minus 1. So it's minus 7, minus 1, minus 7, minus 1, minus 7, minus 1. And then my sulfur, how many associated electrons? 4. You're a pro at this. And so that gives me a plus 2. Now, this here is my structure on my polyatomic ion. I'm just going to go like this. If we add up all the formal charges, minus 1, minus 1, minus 1, minus 1, that's a minus 4, plus a positive 2 gives me a minus 2. My formal charges add up. That's just kind of neat. Okay. Now the question is this what nature had intended? And we look at these numbers here, it's like, boy, that's a positive 2. Last time we saw that, it was pukey. And so, is this really the best that we could do? Is it possible that we could do some other structure that would give us better formal charges? The answer is yes. We could do something different with this. Now, Will, I need somebody smart. I need a top-notch chemistry person. Can you help me out here? Tally. Where's Tally? Wait. Oh, way over here. I'm going to get whiplash. Okay. Tally. I'm going to draw a different structure. Okay? And based off of the chemistry that you know up to this point, you got to let me know when things start looking a little weird. Okay? All right. So here's what I'm going to do. I'm going to start out with my sulfur in the center. And I'm going to make some single bonds like this. Okay? And then I'm going to go, well, I'm going to go like this. Just for fun. Okay. Tally, am I saying that right? Okay, like add things up? Tally. Yes. All right, Tally. What's wrong with this? Not sure? Shh. Have you heard of the octet rule? Yes. What does the octet rule say? Only 8 electrons. How many electrons are on that sulfur? Not 8. Pardon me? There's more than 8. 2, 4, 6, 8, 10, 12. 12, right? Because it's the Dodeca rule, right? It's not the octet rule, it's the Dodeca rule. New rule. Making it up here. You saw it first. All right, well that seems a little weird. That's odd. That's weird. But Tally, let's do our formal charges and such here. So oxygen, we know that oxygen has 6 valence electrons. 6 valence electrons. Sulfur has 6. And then our associated electrons, these ones here are just like we have here. So I'm going to go -7, -7 gives me a -1 and a -1. Now, how about this one here? How many associated electrons tally do I have on that oxygen? 6. All right, so 6. Whoa. All right. And this is the same structure, so I'm just going to go -6 gives me a 0. And then how about that sulfur? How many associated electrons on that sulfur? 6. Yep. So 6 minus 6 equals 0. Huh. And then if I go like this, do all of those formal charges add up to a -2? Yes, they do. And are these formal charges closer to 0 than this one? Yes, they are. Yes, they are. So this one is good. This one is bad. Okay. Is bad. And you go, wait a minute, but that's breaking the octet rule. This is like everything I ever learned. This is like dogs and cats getting along. But this is the way nature intended it. This is what nature likes. So the octet rule is more of a guideline. And if you're like me, Tally, you're probably thinking, well, how do I know when to follow the octet rule and when to just kind of go do my own thing? As long as we follow our rules. So we have the 5 rules for drawing Lewis structures, then we have our formal charges. And if we follow our rules for doing Lewis structures and our formal charges, we're going to be okay. We'll be all right. And fortunately, we're going to have some practice on this too. Try to get this all solidified in our mind's eye. Right. Will, thank you for finding such smart people. This is awesome, right? Or no, was that you? No, that was Will? Yeah. All these smart people. I'm so happy. Welcome back, everybody, and hello to our online students. Today what we're going to do is we're going to take a look at something called formal charges. Formal charges was this thing that happened when I went from being 17 to 18. You may have heard of this. When you're 17, nothing is on your permanent record, but when you turn 18, formal charges stick. You know, the microphone can't pick that up. You got to laugh louder. Okay, thank you. All right.